Okay, so what if we had a wire that has current flowing in the wire and it's in a region where there's a magnetic field? Current is flowing charges, right? Current is a bunch of moving charged particles. When we pretend that we have current, so we draw current as the direction that positive charges would go. And so basically a current carrying wire that's in a region with a magnetic field will feel a magnetic force. And I'm not going to do the derivation of this, but the magnetic force ends up being the amount of the current times, this is a length vector crossed with the magnetic field, where the length vector is a vector that has the magnitude, which is the length of the wire, and the direction comes from the direction of the current. So you have a length vector. And then, again, we're going to do a cross product to get the direction of this. So we put our fingers in the direction of the current and then cross them into the direction of the magnetic field. So in this picture that I've got drawn here, the force would be coming out. So we'd end up with a force here, which would be coming out of the board or out of the screen, because we have our fingers again in the direction of the current this way, and then we turn them towards the direction of the magnetic field, and my thumb will be pointing out of the board. Let's do number 39. It says a horizontal power line carries a current of 5,000 amps from south to north. So let me draw. This is supposed to be the ground. And I have a power line which is going like this, and it has a current like this. And so this direction is north, this direction is south. That means that basically east is out of the board or out of the screen, and west is into the screen. All right, if you can imagine this, looking at this from above, we would have north, and then east would be towards out of the screen, and west is into the screen. Just some things here. All right, and then again, our current, so this is supposed to be our current, which is 5,000 amps, which is a lot of current. And it says the Earth's magnetic field, which is has a magnitude of 60 microteslas, is directed towards the north and inclined downward at 70 degrees to the horizontal. And so I'm going to draw the magnetic field. So the magnetic field is like this. These are all supposed to be parallel to one another. So here's my magnetic field, and the angle that it makes to the horizontal is 70 degrees. So it's directed downward at 70 degrees to the horizontal. And it says, find the magnitude and direction of the magnetic force on 100 meters. So the length is 100 meters. Let's put in another piece of paper here. All right, so the magnitude of our force is just the magnitude of the current, the magnitude of the length, the magnitude of the magnetic field, and then again the sine of the angle, where this is the angle between the current and the magnetic field. Well, that's our 70 degrees. So if we put in all of our values here, 5,000 amps, 100 meters, 60 microteslas, and the sine of 70. Let me pause this. Again, a magnitude of the force is 28.2 newtons. Now, when I do the right-hand rule here, so right-hand rule number 1, again, I'm going to put my fingers of my right hand in the current direction, which is to the north. And then I'm going to curl those fingers to the magnetic field direction. Now for me to do that, my hand is, I'm going to have my thumb basically pointing into the screen. If I have my thumb out, I can't curl my fingers down to that magnetic field. So I have my fingers along to the right, with my thumb basically pointing towards the screen. And then I can curl my fingers down to the magnetic field. Right, so I'm basically say here is for my fingers at first, and then I curl them down. My thumb has to be in to the screen. So that tells me that the F sub B is into the screen, but that's also to the west. So the direction is to the west. This power line would have a force basically pushing it with 28.2 newtons on 100 meters of it towards the west. Okay. How about if we had a loop of wire with a current going through it? And then I'm also got it attached in an axis there that's going right through the middle of its basically. So here's my loop of wire with the blue current going through it. And then I also basically have it on like a pole or something here in the middle. So there's this axis that it's on. It's attached in the middle. And I've got this, again, the purple magnetic field lines. So looking here, let's look at this side. So when the current is moving here up through here on the right-hand side, if I do the right-hand rule on this, I'm going to get that my fingers are moving in the current direction, and then I'll curl my fingers in the magnetic field direction. So the magnetic force on this side right here, on this right-hand side, the magnetic force is into the screen. Here, there's no magnetic force on the top, right? The angle here between the current and the magnetic field is 180. The sine of 180 is 0. There's no magnetic force there. And there's also no magnetic force on the bottom. But on the left-hand side, here, again, I put my fingers and then I try to curl it. This has got a magnetic force which is out of the screen. So this side is being pushed out of the screen. This side is being pushed into the screen. This is going to cause this object, this coil, to rotate. One side's being pushed in, one side's being pushed out. This is going to cause this thing to rotate around the axis. A force that makes something rotate is a torque. There's a torque that causes our loop to rotate. That's what torques do. And it doesn't, I'm not going to do the derivation of this, but it doesn't matter what shape the loop is in. It doesn't have to be this square. It could be a loop, a circle, or an oval. It doesn't really matter what it is. The magnitude of our torque is always going to be capital N, which is the number of times your wire has been wrapped around. So this is just one loop of wire, but you could wrap it around multiple times, right? And so that you actually have multiple torques going on here. The amount of the current, the area inside the loop. So in this case, this is the area. How much is inside the loop? How much area is inside there? Again, magnetic field. And then the angle between the area vector and the magnetic field. So the area vector in this situation, let me get rid of these here. There's a lot going on without adding all that in there. My magnetic fields went away. The area vector in this situation, so the way you get the direction of the area vector is you basically curl your fingers in the current direction. And so for me, I take my right hand and I basically curl it along the current. And when I do that, my thumb sticks out. So the area vector here comes straight out. It is out of this thing. And so the angle between the magnetic field and the area vector here is 90 degrees in the orientation that it's in right now. Let's do this example. This is the one I want y'all to do anyway. So this is number 49. It shows a loop in our XY plane, or XY volume, and it says what's in the XY plane. And it says that it has 20 turns. So this 20 turn, that's this. It's basically saying that the wire goes around 20 times. The dimensions of this are 10 centimeters by 5 centimeters. So our area is going to be, this. Our area is the dimensions of this thing as we multiply the area length times the width. So 0.1 times 0.05. We have an area of this. We have a current of 0.1 amp. And then it says it's mounted in the XY plane at an angle of theta equals 30 to the direction of the magnetic field, which it tells us that the magnetic field's value is half a Tesla. Now, if I try to get my area vector here, so again, I want to know the magnitude of my torque. I need to know that at least first. I want to know in unit vector notation what's the torque acting on the magnetic field, but I can get the magnitude by doing this, right? NIAB sine of phi. But first I need to know the angle between it. It's not necessarily the 30 degrees. So if I curl my fingers in this current direction, if I do that, my thumb is pointing along the negative z axis. If I do that, the area vector goes like this. If I do it, it goes along that way. So my area vector is in the negative k direction. And the angle between this direction, which is the way the A is going, and the magnetic field, that's this phi. So phi is going to be 90 plus 30, or 120 degrees. Doesn't really make a difference. Sine of 30 and sine of 120 is the same number, but that's the actual angle. And so I can get the magnitude here, 20 0.10 amps, 5 times 10 to the negative 3 meters squared, half a Tesla, and sine of 120. Remember that the units for torque are Newton meters, which is technically the same thing as a joule, but that's not what we write down for that. So then the direction of this torque. We used to talk about torque in terms of clockwise and counterclockwise, but we can also do it in terms of this cross product. So technically torque here can be written as this thing. It's this magnetic moment, magnetic dipole moment, which is essentially the area vector crossed times a bunch of these sort of constants crossed with the magnetic field vector. So if I wanted to the direction, I want So again, we could write it this way. N-I A cross B. So my area vector crossed with my magnetic field vector. If I do that right-hand rule, so if I put my fingers in the direction of the area vector, and then I spin them towards the direction of the magnetic field vector, my thumb is pointed down. My thumb is pointed down, and that is the negative j hat direction. So this is directed in the negative y direction. So the torque is negative 4.33 times 10 to the negative 3 Newton meters j hat. All right, that's really the only example I think I have you guys do with that. Maybe you guys do number 43. I don't want you to get too stressed about these torques on these loops. It's probably the biggest fight is just trying to imagine all of these things. All right, that's all for chapter 28. I'm going to move on and do a couple of videos on chapter 29.